All right, today we're going to be talking about conservative forces and how they relate to potential energy. So we've discussed this before. If we are at a point A and we have another point B, and if it takes a certain amount of work to go from, and if it's under a conservative force, that the amount of work, if we just go straight from point A to point B in a straight line, okay, assume that's straight, and that'll take a certain amount of work, W. But the cool thing about it is, so long as whatever amount of work that is, it doesn't matter. We could take this path here, okay, and wind up at B. And as long as we end up at B, then the amount of work is still the same. It's a constant amount of work. That our work is path independent. And the same thing applies that if we start at A and we go around, we wander, and then we come back over here, and then we wind up back at A. If we wind up back in the same spot, then the amount of work that was done is zero. The amount of work that, the positive work that it takes to go away from that spot is equal to the negative work it takes to return to it. So it's the total amount with a conservative force, the total work equals zero. And we kind of played with this the other day. Those of you that stuck around after class, we played with our pendulum. No, we played with the class pendulum. Right. Okay. So, so we've got our pendulum here, and it'll swing out here, and it'll go back and forth like this. And assuming that there is no air resistance. And actually, let's assume that right down here, this point down at the bottom is our zero, is where U equals zero. That the potential energy in this pendulum is going to be given to us by the height of the pendulum above the lowest point. That would be our change in potential, okay, as it swings. And if there were no air resistance, if the only force acting on this thing would gravity, this would oscillate forever. Okay. Now, in real life, we don't have that. There's always some kind of internal friction, or if we just swing it in here, and there's the friction of the string hanging on the hook, and there'd be a little bit of friction slowing it down eventually. Or the way we have the ball in here suspended is with a very aerodynamically inefficient mesh, a plastic mesh that just creates all kinds of drag around it, and so it doesn't swing forever. So that's it. I would like to come up with a more perfect pendulum. Perhaps if we evacuate the air out of the classroom so everybody hold your breath. Okay. Not to mention the fact that your blood would start to boil and your eyes would pop out of your head if you entered a vacuum. Those are just minor hazards that we have to avoid. Right, now, this will oscillate forever. However, that is assuming that there are no external forces, that all of our external forces would equal zero. Okay, if we do start getting these external forces, like we said, the air resistance, the friction of the string on at the swing point of the pendulum, then we start to slow down, and we have a dampening effect on the oscillation, which we'll get to later on in the semester. Okay, so the main equation that we want to talk about here is the first one. That if there is, what do I want to say? That the work done by a non-conservative force is equal to our change in mechanical energy. Okay, and this covers everything. All of our contingencies are included right here. Okay, so our total kinetic plus our total potential plus, at our initial, and then we have our change in our total kinetic plus our total potential. The change in that is going to, if there is a change in that, that means that there was a non-conservative force, and the work done by that non-conservative force equals that change in the energy. So that it's a really powerful concept, and it makes a lot of things easier that we're going to be doing later on. We are going to be working right now with just two conservative forces, though, gravity and springs. Okay, and we will generally identify when we have no non-conservative forces at play. Okay. So we're going to take a book. Let's take our book here. So we're going to have a surface. All right, and we have a book over our surface. Please do not assume that just because my drawing is not horizontal, that's not what I mean. So we have a book, and this book has mg acting on it, and it falls to a height here. So it's got initial y and a final y, and so this distance right here is our delta y. Okay, and when this happens, this object is going to, it's going to lose some of its potential energy if it falls towards the ground. It has a greater potential the further away it is from the ground than it is close to it. We've talked about this with I believe we talked about cringe. Have we talked about cringeworthiness in here? No. Something being cringeworthy? Okay, well then here is. Well, I'll demonstrate it for you here in a second. I'll pause the video, and you guys will have to have me demonstrate if you missed this in class. Okay, so that's cringeworthiness. You guys come on, once again, come. We'll talk about cringeworthy when those of you who watch the video we're not privy to the classroom instruction or the classroom demonstration. Just ask Nor about that. He'll tell you everything there is. So, well, in this case, because all of our potential right here, and we lose this potential, that's going to go right into our change in potential. Okay, but the work done by a conservative force guys, the work done by a conservative force, okay, is equal to the negative change in potential. If we go from this point up here to this point down here, okay, we are losing potential energy. But what else do we know about, the other thing we know about this is off to the side, because we know that work is also equal to our change in kinetic energy. Okay, so this amount right here that it's losing in potential is equal to the amount that it's gaining in kinetic. And so you can take a cup of, imagine you've got your total amount of energy in 2 cups of energy, and you can pour them back and forth. Okay, when you have a conservative force, that if you have potential, it can turn into kinetic directly, and if you have kinetic, you can turn potential, and they're two amounts of two amounts of the same stuff. Okay, now we want to go somewhere with this, and we're going to give you a better definition, or we now get to enter the physics C portion of our discussion with this. Because the work of a conservative force equals negative delta U, okay, we also know that work equals the integral of our conservative force dot dr. All right, so that means that our negative, well, I'm going to move the negative to the other side, so we'll have this delta U is equal to negative integral of conservative force, that's a C, negative FC dot dr. All right, now, because there is only one direction that is truly relevant to our conservative force here, okay, is either towards the source of the force, I rhymed, or away from the source of the force. Okay, because the force, we all know, is something that runs through all of us, is a natural part of nature, and so we must, be with the force, or may the force be with you. Okay. I kill myself sometimes. Okay. So because it's only relevant in one particular direction, that the force in the y direction dot dy, okay, or fy dy is still going to equal our our delta U. But we can even go further with this. If we get rid of the integral, what else can we do? If we get rid of this integral, this is no longer a total delta. This becomes du. Du equals negative fy dy. Okay, so think about this. The differential change in potential energy is equal to the force, because it is a constant force, times the differential change in height. You follow me here? All right. So, our differential incremental change in potential equals our incremental change in height times the force times its non-conservative force. We can then rewrite this, okay, and we get our, so we can move the dy over here, and we get our force in the y direction is going to equal negative du dy. Okay, so think about this for a sec. That the force on an object is the position-dependent change of our change in our potential energy. You follow me there? Okay. It is the rate of change, not the time rate, but the position rate of change of our potential. So as we change position, how does our potential change? Okay, and that's related, that's given to us by the force, by the conservative force that is acting on this object. So let's take our potential energy. U equals mgy. Okay, well, we're going to run this operator on it. That negative du dy is going to equal negative d dy, this operator, on mgy. Well, this is pretty straightforward. This is one of the easiest derivatives you're ever going to do. Okay, because d dy of mgy, those two are constants, and y vanishes to 1 when we take the derivative. So negative du dy equals the force in the y direction, which is going to equal negative mg, which is our force of gravity. Okay, so we're going to try something. We're going to extend this to another situation. Okay, we have a wall here. And that is, I kind of need that one to be level, so let's try that again. And we will make a real straight line this time. All right, and here's our wall and our surface. All right, and we have a, unfortunately I don't have my car available to us, my sedan, so we just have to go back with a crate. Yeah, my sedan's in the shop. It's pretty old. It's tough to find parts for it, so we go back to our crate. What's that? Yes, like my real car. So shut the heck up, Mr. Hunter. don't you shade on my car. All right. Okay. My car is much more stylish than just a crate. This is probably one of those Scion XAs, right? No, oh God, those are just hideous. So don't tell me that my car is a box. Okay, and those of you that missed that part of the lecture, I just went on a expletive-laced tirade about people calling my car a box. So now we have a crate. Okay, our crate is a distance x. Okay, or this is our equilibrium point here. Okay, so our potential energy given by this guy is Okay, so our U, potential energy from our conservative force. Well, in this particular case, the U of a spring is 1/2 kx squared. So our force of the spring is going to equal negative d dx of 1/2 kx squared. Yeah? Okay, pretty reasonable. All right, so our f of x, okay, our force in relation to x is then going to be, well, let's see, the derivative of this is negative 1/2 k, okay, times this is going to be 2x. Well, then the 1/2s cancel with the 2, and so we wind up with negative kx is our force. So, and we've discovered that's Hooke's law, right? So we have the potential energy of a spring, and we're able to derive Hooke's law from the potential energy of a spring. So this is something that this is, there's a good chance that you might see this again soon, like maybe on a test or perhaps. But this sort of thing is definitely on your AP test, so be ready for this. Okay, now, at this point, we're gonna venture off of the beaten path to a degree here. I'm going to teach you a little bit of math that is not. You're not even going to get it in your Calc BC. It is. Are you guys taking math off campus? Math somewhere else? You are? Okay. This is called. You'll get this in the next level of math. This is called. This concept is called the gradient. Okay, and this is a very powerful tool, particularly for physicists. And this is, I saw some of you guys, your eyes light up the other day when I talked, we were going to do a partial derivative. Okay, that we're actually going to do partial derivatives right here. And it's actually really cool, and it makes things way easier, okay, for certain things that we do in physics, particularly if we have things that change in 3 dimensions. Okay, and what this winds up being is, and I'll write it out for you. This is not on the test. It's not on the test. Okay, but I will tell you that this gradient of our potential energy, the negative gradient of the potential energy equals the conservative force. Okay, but it's the vector. Okay, so everything we have up here, that this du dx or du dy equals our force in that direction. If we extend it to the vector, this is what happens here. This would be a negative, yes. Negative gradient u equals, okay, so this is what it equals, and it's going to look fancy, but it's really, really not that hard. It's this lowercase delta, okay, this d-looking thing is the partial derivative. No, not that d, the other d. dz k hat. Okay, this is what it is. So it's now this is a scalar. Okay, that your force will be a scalar, and you have to do something else to find your direction. But you don't really need it, because what you're calculating here is your potential. You're going back and forth between your force vector, okay, and your potential. So here's how it works. For example, let's take our u function, u of xy. Okay, yes, it is a function in 2 variables, equals 3xy. Okay, so this is our potential energy function for it. All right, here's how it works. The gradient of this, all right, so let's say we take du dx. Okay, this is just the derivative of this dx. Well, this is going to become 3y plus 3x dy dx, right? We have to do a partial implicit differentiation kind of thing, right? Okay. Too much work. This sucks. Okay. What you are allowed to do, and this is the beauty of this, you are allowed, if you take a partial differentiation, everything else aside from what you're differentiating stays constant. So, the partial derivative of u of du dx equals, well, if x isn't constant but everything else is, this just becomes 3y. That's it. 3y is the constant. X, the derivative of x is x, and the derivative of x is 1. Okay. Du dy, I'm sorry, partial u, gosh darn it, partial u over partial y equals 3x. Okay, so the force, okay, this conservative force is going to equal du, or partial u partial x I hat plus partial u partial y j hat, but it's negative, right? Because this is the gradient, so it'd be the negative, sorry, of all of this. All right, so this winds up being negative 3y minus 3x, and that would be the position-dependent force based on where your x and y is on that potential energy. It's really powerful. It's not on the test, but I thought you guys would be interested in this technique, and that it actually it helps simplify a lot of complicated systems for doing this. So it's really pretty cool. Okay, so that brings us to the last thing that we're going to talk about here. And it's if we graph this. So we're going to have we're going to step a graph here. Ooh. Shift. There we go. There's our line. Yeah, lines are kind of hard. I have one program that you have to do. You have to draw the line first and then click. It's like when I'm doing it on the iPad. I have to draw the line, then constrain it by doing a second finger, and then it makes the line again. But this program, I have to hit Shift first and then draw the line. So I have to change brain techniques there. Okay. Imagine we have a bowl. And our bowl looks like this. And here's the surface of the bowl. Okay, it is a cross section of a bundt cake pan, if you will. You guys have seen bundt cake before? You ain't never seen bundt cake before? Okay, it essentially bakes cakes into a half torus.
A big donut.
Yeah. Yes, it's a big donut, Mr. Hunter. Yes, that is. But I prefer using the fancy term called a torus, which essentially is it's a circle that is rotated around. It's a torus. No, not a Gemini, a torus. So it's it's a circle that's rotated around an axis. So yes, a donut, but a donut with varying size hole. Okay, all right. But it's like a perfect donut. It's not like flat and you see like the thing. Okay. Anyways, it's a perfect donut.
Utopian donut.
We have an object right here. In fact, here's our object. We're going to add some color to this. It has right now its initial. Oh, I'm sorry. The axes for this. This is u. This is our potential, and this is our position. Okay, and this height right here is u naught. Now, if it starts at rest, this is not only u naught, it also equals what? Well, if u naught, okay, is there, k naught is, okay, or let's call it initial, however, okay, if this is u initial, then our k initial, if it starts at rest, our k initial would be what? It would be 0, right? So, if our K initial is 0, and this is our initial potential energy, this whole thing combined, this U initial also equals our initial energy. Our total initial mechanical energy is given by that potential right there. All right. Now, if we allow this to roll, what direction is it going to roll? Down. But if we actually take the direction, it's going to be in that direction, yes? Okay. How do we determine that direction?
Derivative.
We take the derivative of the function, because the direction would be the slope of the line, yes? Oh, well, what would the slope of this line be? The slope of this line would be du dx. Oh, wait a second. That looks familiar, doesn't it? We were just talking about du dx. Right? Du dx is the force. The slope of this line equals du dx, which equals the negative of the force, of the conservative force. Ah, very nice. Right? Okay. So, a couple of cool things. The slope. Now, what happens if our ball gets to here? Okay, and we take the ball and we have an external force and we stop it at this point right here. What's the slope of the line? It's 0, right? It's at the ball. Okay. When the slope of this line equals 0, what forces are acting on it? None. There are no forces. The conservative force, right? If du dx equals 0, then there's no force, right? Okay. If the slope is 0, there's no force. There's no net force acting on our ball right here. Okay. Okay. Where else could we find this? Okay. We can find one here. We could also find one here. Now, all three of these are places of. Yes, they are all extrema. Relative extrema. Yes, they are all very good. They are all relative extrema. They are also points of, okay, physics term here. This is an actual physical concept. When you see objects like this, and the ironic thing is that when you graph potential energy versus position, okay, it actually looks like the real situation. That if you look at an object that's undergoing a conservative force, if you think gravity, okay, this is you can imagine this is an actual boulder at the bottom of an actual hill. Okay? And here's why. We'll explain that in a sec. These are points of equilibrium. They are points of equilibrium. Now, to this guy right here, and this guy right here, if I push him up the hill a little bit, and I let him go, where's he going to go? If I push him up and I let him go, he's going to roll back, right? Same thing with this guy right here. If I push him up the hill a little bit, he's going to go back. If I push him up the hill a little bit, he's going to roll back. How can we determine, mathematically, how do we determine these points of relative minimums? We take the second derivative, right? Okay, and we do a concave test. How do we determine whether something is concave up? Okay. Okay, well, what do we get? That the second derivative is...
I mean, if it's concave up.
Okay, if the concave up, then the second derivative is...
Value at that.
Okay. All right, we're struggling with it. D squared dx squared of u, if the second derivative of the potential is greater than 0. Oh, where's my... Oh, that sucks. I got to do a setting here. I forgot to do that. Options. Oh, where are my options? What the heck? All right. Still didn't work. Okay, if our second derivative, gentlemen, is greater than 0, if our second derivative is greater than 0, then we have what's called a stable equilibrium. This is a ginormous concept in the entirety of the physical world. Stable equilibrium. Okay. The idea of noble gases having stable electron configurations. Okay. That's because other electron configurations have potential energies higher than these points in their potential energy function. Okay, when they have all of the electrons, and if you guys remember in your chemistry, when you have all of the electrons in your S and P orbitals and those are filled, those are stable electron configurations. They are at their lowest potential energy points for electrons in those orbitals. Okay, this is what we're talking about here. Those are stable equilibria. Now, not all equilibria are created equal. This guy right here is at an equilibrium. If you put this dude right there on top of the hill, okay, it'll stay there. But if you give him a little nudge that way or give him a little nudge that way, where is he going to go? He'll roll away from the equilibrium. So at this point, this is, balancing on the head of a pin. This is stacking golf balls together. Okay, these are those improbable rock formations out in the desert that are, that they've been worn away. And so there's a little teeny tiny thing holding a huge boulder. You've seen pictures of these. Those are stable equilibriums. Those are places where Noor would walk under and cringe. All right, so would we all, Noor. So would we all. So the second derivative of our potential energy is less than 0. This would be unstable. All right. So, one more time. If du dx equals 0, then we have an equilibrium. All right. So, if our first derivative equals 0, then we have an equilibrium. If the second derivative, if it is concave up, then it is stable. If it is concave down, it is unstable. And that, my friends, is the end of today's lecture. So.